Hello, my name is Eugenie, and I'm excited to share with you today my research on transgenerational dopamine activity genes linked to delinquent behavior and the therapeutic potential of natural products. In today's digital world, I've witnessed firsthand how social media captivates not only my peers but myself. Platforms like TikTok, Instagram, and Twitter are designed to exploit our brain's dopamine system. Each notification, like, or comment triggers a dopamine boost, creating a cycle of instant rewards that can be highly addictive. And this digital drug has become an integral part of daily life, especially among teens, raising concerns about its impact on dopamine regulation and its potential to exacerbate mental health issues. But dopamine, a neurotransmitter crucial for cognitive function, holds an influence that isn't simply about what happens at the moment, but also of how it's encoded into our genes. And certain gene variants heighten an individual's response to dopamine, making them more sensitive to reward-driven behaviors. As shown in Figure 1, these genetic predispositions are often amplified in high-risk environments, indicating that genetic vulnerabilities combined with environmental factors can shape an individual's likelihood of engaging in delinquent behaviors. So this led me to ask, could genetic factors be influenced in this cycle, not simply respond to their environment but genetically altered and passed down? So my research delves into the genetic mechanisms behind dopamine release and its potential link to delinquent behaviors. I used two biological models. First, by analyzing gene expression in Drosophila melanogaster under dopamine exposure, it allows an organism-level approach and insight into inheritance across generations. Second, using human brain cells, especially SK and MC cell, exposed to dopamine or lipopolysaccharide (LPS), a pro-inflammatory agent, I directly investigate dopamine's cognitive influence under stimulation of inflammatory response in the central nervous system. And to mitigate these impacts, I looked for a biologic solution easily accessible and safe through common food or teas. I explored natural products known for their neuroprotective and cognitive properties, including turmeric, curcumine, ashwagandha, shatavari, cinnamon powder, and echinopanax powder. Now let's dive into the methodology. In Figure 2, Drosophila were exposed to dopamine through cotton tip submerged in dopamine solution, and as shown in Figure 3, human brain cells were exposed to dopamine or LPS, and then both biomodels were then treated with natural products to evaluate their potential in restoring gene expression disrupted by dopamine or LPS exposure. And as shown in Figures 4 to 7, new psychological biomarker gene expressions were examined through RNA extraction, cDNA synthesis, PCR, and gel electrophoresis. Then the resulting gel was analyzed using a GelDoc imaging system and quantified with ImageJ software. So in Drosophila, genes like FOXP, SCRT, G9A, and PER2 are essential for regulating neural and behavioral functions. FOXP plays a role in social communication, while SCRT functions as a serotonin transporter gene. G9A regulates stress responses, and PER2 is associated with mood disorders. In humans, genes like BDNF, D81, and SOC6A4 play similar roles in dopamine regulation and mood stability. BDNF affects both cognition and mood, while D81 serves as a dopamine transporter gene. And SOC6A4, like SCRT in Drosophila, is a serotonin transporter. These genes, while species-specific, demonstrate how neurotransmitter pathways are conserved across species. So gene analysis in Drosophila examined the intergenerational effects of dopamine exposure. And this part stemmed from a personal experience, watching a friend's gaming addiction reflect that of his parent. It sparked my curiosity about such inherited behaviors. Remarkably, as shown in Figure 8a, the first generation exposed to dopamine showed a significant 2 to 3-fold increase in expression levels of G9A, SCRT, and PER2, while FOXP decreased to a 0.68-fold. But what truly stunned was the second generation. Despite not being directly exposed to dopamine, it exhibited an even more pronounced amplification across all 4 genes, with the previously decreased FOXP also upregulated to a 1.8-fold. And notably, SCRT, which had already shown the highest increase in the first generation, rose dramatically from a 3.09-fold to a 14.87-fold in the second generation. Next, I tested various natural products to assess their ability to normalize the heightened gene expression due to dopamine exposure. Most of my selected natural products were effective in mitigating these elevated levels. As shown in Figure 9a, cinnamon was most effective in restoring FOXP expressions, while turmeric and shatavari were effective in reducing G9A and PER2 expressions. Some natural products like echinopanax for G9A and cinnamon for PER2 exceeded control levels, suggesting potential regulatory effects beyond normalization. SCRT, however, being highly sensitive to dopamine, remained elevated across all treatments, with reductions being partial rather than complete. The effects of dopamine were this time tested directly in human brain cells where there were different patterns. Dopamine downregulated all three genes compared to control. BDNF and SO66A4 showed a milder decrease, while DAT1 exhibited a drastic 95% reduction, indicating a severe disruption in dopamine transport activity. And these results contrast with Drosophila, where gene expression was upregulated, suggesting that human brain cells may downregulate gene activity as a protective mechanism against neurotoxicity, maintaining homeostasis. And for natural products, cinnamon significantly restored BDNF expression, yet DAT1 remained drastically reduced, remaining challenging to restore with only moderate improvements observed across treatment. And for SO66A4, as shown in Figure 12C, ashwagandha and cinnamon further reduced expression below the dopamine exposed level. While cinnamon potentially benefits other pathways, it might have competitive interactions and side effects specific to serotonin transporter regulation. So intrigued by these differing results, I used LPS to mimic stress signaling in the central nervous system to further exacerbate such results and observed an overall amplification from the previous dopamine setting. In this context, natural products demonstrated their potential to restore gene expression balance as well. Compared with the dopamine setting, all gene levels exhibited an increase, upregulated BDNF moderately for DAT1 and exceeded control levels for SO66A4. However, DAT1, despite some recovery, showed a decline, indicating a significantly outlined result. Perhaps as a feedback response due to an engulf of such expression levels, it ended up decreasing it back down. This suggests that while dopamine disrupts key neuropsychological pathways, LPS may trigger a series of adaptive responses designed to protect the neurons and restore balance. And for natural products, turmeric, acantopanax, and shatavari show moderate increases across biomarker gene. So overall, the research highlights the potential of natural products in mitigating the effects of dopamine dysregulation. In Drosophila, dopamine exposure significantly upregulated gene levels, which is amplified across generations. And these disruptions may impair mood, communication, and serotonin regulation, contributing to risk-taking behaviors often seen in delinquent individuals. And natural products, particularly cinnamon, turmeric, and shatavari, showed strong potential to reverse these effects. In human cells, dopamine decreased gene expression while LPS increased it. Yet DAT1 remained suppressed across all conditions. And natural products such as cinnamon, turmeric, shatavari, and acantopanax proved effective. So to conclude, dopamine is not inherently bad or good, and its effect can be highly context-dependent. But my research highlights how dopamine behaves under different conditions, and the dysregulation of dopamine-related genes can contribute to increased risk-taking and aggressive behaviors often seen in delinquent individuals. Encouragingly, natural products may offer a safe and accessible way to modulate gene expression, providing a possible therapeutic approach to reducing delinquency and improving mental health in our increasingly digital world. Thank you for listening.